Hello guys, I apologize for the delay. Hello stream. We're rocking with the MacBook Pro camera. I used to be the head of education, now I'm the vice president. We're gonna get this show on the road because we are severely behind with that. It don't matter. It don't matter. Can I get a round of applause, please? It don't matter. Welcome to RITSEC. This is your weekly fun time. If you guys are in the Discord, please join the Discord. I would assume you guys are in there already. That's where we post our announcements and we share and we communicate and we talk about security. Please sign in. Is signing up? Do I have to do that real quick? Let me sign up. Thank you. Give me literally 10 seconds to sign in. And you guys can sign on in because that's where we get pizza. Yeah. Okay. But yeah, it's open. There we go. Thank you, Igor. You guys need to check the calendar. That's how it gets updated. All our fun swag events, like our lunch work trip, that's tomorrow. You guys, if you're going, need to be here at 10:30 a.m. in the circle. The announcement will be coming out soon because I learned how to be a Discord moderator 10 minutes ago. You guys should also join the mailing list. That's how you get those sweet, just, oh my goodness. The emails, once a week, Raina sends those out. It has all the stuff on there, all the updates, all the research presentations, all the links to the applications for research presentations so you guys can present and share your work. Sign up, please. And feedback. We'd like to hear your feedback. We're always trying to improve. The only way to get better is to connect with you guys because we're doing this for you guys. That's the link for it. That's the URL. Announcements. Weiss's CTF. So Weiss's is hosting a CTF this Friday, Friday, October 20th, starting at 5 p.m. to Sunday, October 22nd at 5 p.m. It's a good time. If you have any questions, please DM Rachel. Rachel is the vice president for Weiss's. Yeah, I think so. It's a beginner-friendly, focused CTF. You guys are welcome to participate. It's not only exclusive to women and women adjacent, but it's nice. P.S. I am still accepting challenges. However, challenges are due October 1st. Please give Rachel challenges if you told her and you win the challenges. There's nothing worse than just telling lies to Rachel. It's really bad. Don't do that. My goodness. RITSEC. Where's Jack at? You want to talk about it? Come here real quick. Run here. Come here now. Jack is the RITSEC CA.
Hey guys, so sorry, forgot how sensitive it was. So IRSEC is November 4th. Black team has officially been picked, so yep. We'll be opening up a white team signups relatively soon, and then we will also have. I will announce the dates for the blue team workshops, which will be on Saturdays, roughly the beginning of the day.
If you guys aren't familiar, IRSEC is our in-house career competition that's kind of beginner oriented. There are only RIT students allowed to compete, and you will be competing against RITSEC red team. You're allowed to sign up by yourself or with a quote of 5. I highly recommend asking around to get that to the 5 sorted out early. It's real fun when you're competing with your friends. But yeah, that is blue team sign up URL or QR code. Please scan that. Do you guys need to scan that? Do you need to scan it?
It's also in the announcements.
It's also in the announcements, yeah. But the deadline for this is October 4th at 11:59 p.m. Eastern Standard Time. So please sign up. Also, thank you, Trace Cat. I was going to say that. Junior's obsolete and junior need signups signups in today. So if you guys want to submit that application, this is your last chance today at 11:59. Be there or be square. Yes. Yes. There should be an announcement, and if not, the QR code is right there. Yeah. DM Michael Scowls actually about obsolete or junior obsolete, and DM Alex Noble if you guys have any questions regarding junior tech lead. Oh, my favorite. Okay, web admin applications have been open for a week now. They close on the 6th of October, so please apply. I'm begging, please apply. You guys get to manage the RITSEC website and be under my control, which is so fun. That's the okay, no, it didn't go. Okay, yeah, that's the QR code. There's also a Google Form link on the bottom. That closes October 6th at 11:59 p.m. Please apply. It's a good old time to be web admin. Also, social media head applications are also open. You guys ever seen our sweet social media post? Yeah, you could be doing that. If you are a fanatic on social media and your presence on social media is very swell and spectacular, yes. What? That's why we're passing an audio through that, right? Can the Twitch stream hear me? Because I know I'm muted on my laptop, but stream should be getting a different audio input. They get the input from this, and it goes to our stream laptop. We're good. I appreciate it, though. Thank you, Izzy. But yeah, social media. If you want to run our social media and make those sweet, splendid social media posts, sign up. You'll be under my control, but you'll be under someone else's control. Oh, this is my favorite part. Oh, okay. Red Team Recruiting and Weissman Speaker Event. We're essentially having a diversity and inclusion event with Red Team and Weissman on October 5th in Galveston 1400. Is that this room? 1400? No.
No, it's the big conference
room. Oh, it's the atrium, dude. These room numbers confuse me. Yeah, we're having it. Stella Lee is coming to present, and it's going to be a good time. I highly encourage you guys to come. We'll be talking about unconscious bias and microaggressions. It'll be a good informative time. Okay. Okay, you guys, come on. I don't have to say this mess. Come on, clap. As I was mentioning before, please follow social media. Our posts are so splendid and terrific. And if you see them, repost them and like them and share them with all your friends because we want to spread the word about security through community. Woo! Okay, so today we are having Professor Weissman present Intro to Networking. Very excited for this one. He did a really good job with it, so everybody give him a round of applause. We're going to do a slight transition stream, so hold on.
So I'm obviously staying on mute also.
Yeah, and we're going to pass it.
Oh jeez. The Streamlabs is what is this one plugged into?
Is that your old challenge?
Oh yeah, just yeah. Perfect.
Cool.
This thing's.
Can I wear it?
Is that one the one that works, or is that one the one that works?
Shoot. No, that's probably this one actually. Yeah, do this one. You hit that button on it. And
Yeah, when it's green, it's on. When it's red, it's off. And yeah, you can.
And
wear
that's
it.
going right to the stream also?
Yep.
Yeah, that'll,
It'll pick up.
and then you're,
Yeah, where I'm muted, it should be picking up. I can go double check.
Testing 1, 2. We go.
Yeah.
All right. I'm gonna cut this short. Get right to the lesson. I usually talk a little bit more about my background. I'll make it really quick. I love talking about networking and cybersecurity. I do it on TV news a lot. I do it on talk radio a lot. I do it in magazines and newspapers a lot. I have 3 books out on the Network Plus and the Security Plus certification, free. Oh, I should say on camera, right? Free for RIT students through the O'Reilly Learning Platform. I don't want your money. You can use my books and you can get certified in Network Plus and Security Plus. Go to the O'Reilly page, put in Jonathan Weissman and Security Plus or Network Plus, pop in your RIT creds and enjoy. I have 47 high-level industry certifications. I'm never not studying for certification, so I'm still a student. You guys are a student, and of course, in the world of networking and cybersecurity, the learning process is never ending. If you ever feel that you've learned all that there is to learn, you're going to become obsolete and undesirable in a very quick amount of time. I went through the whole schooling system myself, but in New York City, and when I moved upstate in 2006, people were like, oh yeah, you're going to go to New York? And I was like, well, aren't we in New York? But I guess it's not really New York, but New York City is New York, but I am a New York City boy. I have taught in a few other colleges. I'm currently teaching in a few other colleges as well, and I have 11 teaching honors and awards. The big 3 at RIT are the highlights of my career. And I'm on social media too, CSC Prof on Instagram and Twitter, and you can get my other socials from there, from my Linktree link. And there's a Weissman 52 YouTube channel with all my media appearances and some great stuff as well. Feel free to subscribe, smash that subscribe button. My kids want me to get as many subscribers as Mr. Beast. Got a little bit more to go to catch up to Mr. Beast, but we're getting there. And speaking of that, we've got a lot of tigers in the Weissman household at home. All right, now for the main presentation. Here we go. Okay. How's the time frame, by the way? Do you want me to finish at the same time, or can I go a little bit beyond?
You can go over.
A little beyond?
An hour 20.
Give me a stop dead time. Drop dead time. Let's do around 25. Okay. So I want to start off with 2 funny stories. You don't see that over there. This way. Okay, just one more question. This is what's going on the stream, and what I'm seeing on my laptop is not. Correct? Because I want to position things. Good. Okay, so everybody have a good summer. It seems like summer is a million years ago. We just turned into the fall. And over the summer, there were a bunch of families that moved into the neighborhood that my family and I live in Brighton, about 12, 15 minutes away. And we became friends with some of the families, and we didn't like some of the other families. They weren't into networking and cybersecurity. So one day I met this guy in Weissman. His name was Bob. And I told my wife about him and his family. They had kids the same ages of our kids, so we wanted to be friends with them. So my wife made a care package for Bob and his family, the Smiths, for me to deliver. Now, this was on a Sunday night. It was the end of July, and my wife put all the chocolates and some of the fruits in there, and she said, Jonathan, deliver this care package to the Smiths. Now, I remember talking to Bob earlier that day in Wegmans, but I forgot which street address, which house he actually lived in. It was not too far from our house, but I wasn't really sure because a bunch of houses had some turnover. So this is what I did on that Sunday night. I took my amplifier. I'm also a musician, so I have a 500-watt amplifier. I brought it outside our house, put it on the front stoop, and I said into the microphone, didn't have to shout with the volume jacked up all the way to 10. I said, Bob Smith, which street house address do you and your family live in? And this was late at night. So I pissed off my wife because I woke up my kids. I pissed off the whole neighborhood because I woke up all the other kids in the neighborhood. Everybody was screaming and people were actually throwing things at me. But I got Bob Smith's attention. And Bob Smith didn't want to be as hated as I was that night. So what he did was he very discreetly walked over to our house and said, it's 123 Main Street. And he went back to his house. And later that night, after finishing up some of the chocolates, don't tell but I ate some of the chocolates from the care package, I delivered the care package to 123 Main Street. and we became good friends, good family friends with the Smiths. That's a cool story, no? So that was one funny story that happened over the summer. Here's another funny story that happened over the summer. My childhood home is in Staten Island, New York. You guys ever hear of Staten Island? Wu-Tang Clan, Impractical Jokers are from Staten Island as well. So we go back every now and then. We visit my family in Staten Island, my wife's family in Philadelphia, Pennsylvania. You guys know the difference between in-laws and outlaws? Outlaws are wanted. So anyway, we visited my family in Staten Island, my childhood home, and the 6-hour or so trip back was fun. We listened to music, and we had these great discussions in the car. Then I'm bringing in the bags from the car, and Noah's bag and Jacob's bag seemed very, very heavy. And I was like, what is this stuff? So I opened up the bags, and inside the bags, each of them had one candlestick holder that my mom used to light Sabbath candles with. And I said, guys, what is this over here? Gold, shiny, diamonds. And they said, Bubby, which is the Jewish term for grandma, Bubby let us have them. So I said, did she really? They said, yeah. So I checked my email, and I saw like 5 or 6 emails from my mom saying, have you seen my candlesticks? So I called her up, and I said, Kit said you can have them. And she said, no, I didn't. I said they could look at them. So what I had to do was I had to get those candlesticks back to my mom and my childhood home in Staten Island, New York. My dad was like, are your kids always this shoplifting oriented? And I said, no! So I looked up the nearest UPS store that was close to our house. It was it's in 12 Corners area. Anybody from Brighton or familiar with Brighton? Not too far from here. So there's a UPS store on the corner of Elmwood Avenue. And what I did was, after Googling for that nearest UPS store, I put my mom's candlesticks holders in a box, round box, and I brought it to the UPS store. And that UPS store was so cool. They took my money, they took my box, and they sent it to a UPS facility, who sent it to another UPS facility. Eventually, it got to my childhood home in Staten Island, and my parents were very happy to receive that package because otherwise Sabbath candles would have had to be in something less grandiose. So, a couple of crazy stories that happened over the summer. Were your summers as eventful as mine? So in terms of networking, in terms of local traffic versus remote traffic, local traffic means that the source of traffic and the destination of traffic are on the same network, which is synonymous with LAN, local area network, synonymous with a term called the broadcast domain. So every time you have traffic to send to a device on your LAN, you, the sender, the source of the traffic, you send it directly. Anytime you have traffic for a device that is not on your LAN, whether it's one network away across the router or 5 or 6 or 10 different networks away, you as the source device, you do not send that traffic directly to the destination. You send it to your default gateway, router interface on your network that's responsible for taking traffic off of your network and bringing traffic from other networks onto your network. Speaking of networking devices, the two big ones, of course, are switches and routers. I like to think of the switch as the connection between different parts of the city. So if you are a data packet and you're going from one port, you're going into one port, you're at RIT. So there's an RIT device connected to the switchboard. I should probably animate this on the screen as well. There's a PC connected to this particular switch port over here. You're at RIT. You go through the switch. You come out another port connected to the Weissman device. And then you go back into the switch port and you are connected to some other item element location here in Henrietta or any place in the general Rochester area, greater Rochester area. Switches are like the streets of a city or a town that connect the various elements of the town together. Hence the devices on a network. So switches connect devices. Switches connect devices that are on the same network. Routers do not connect devices. Routers connect networks. So if you're on the highway and you're on 490, and then from 490 you go to 90, and then from 90 you go to Now, you can go from highway to highway to highway. Think of the router as more of that long distance transformer device, which puts you on one city and then on another city. You can use states, it works the same way. You could use countries and continents, it works the same way, although it'll be a little bit more difficult for those big of the jumps. But the routers don't connect devices. The routers connect the networks, just like the highways go into other highways to connect you to other parts of the country, other states, other cities, other geographical locations. So far, so good? Okay. Now, every device on a network that needs to be thought of as its own entity, its own end device. An end device, END, basically means it's a node. A node basically means you can either be the source or destination of traffic. You can be the starting point of the traffic, or you can be the final destination of traffic. That's a good movie. You guys ever seen the final destination? You can be the final destination of traffic. The way that we organize devices and networks is through these logical IP, stands for Internet Protocol, addresses, which are described with the following adjectives. They are logical. They are software-based. They are hierarchical, which means one part means one thing and one part means something else. And in most cases, they are geographical, which means you can look at a particular IP address and looking at that part that represents the network, you can know which part of the world you're in, and you can even know who your internet service provider is in some cases. The IPv4 addresses are written in dotted decimal notation, which means dotted, got the dots. Decimal doesn't mean the dots. The dot means the dot. The decimal means base 10 over here. The numbers are represented in base 10, the base 10 numbering system. And underneath the hood, of course, everything is a bunch of ones and zeros. So these 8 ones and zeros add up to 172. These 8 ones and zeros add up to 16, and so on and so forth with the last 2 octets. That's what we call those numbers. We don't just say numbers. We say octets because there are 8. Oct is a prefix that means 8, except on the calendar. I think Caesar messed that up. Des usually means 10, but it's the 12th month of the year. So dotted decimal notation is how we represent IP addresses. IPv4 addresses is going to be the focus of my talk, although I am an IPv6 evangelist. I'll tell you more about that later. Been trying to get IPv6 going in the world for the last 10 years, and it's slowly but surely seeing the light of day, but IPv4 will be around for decades, because if it ain't broke, we'll fix it, and that's something that I don't want to talk about right now, because that is what annoys me. This is a flashback to the height of COVID, because the IP address by itself used to be able to identify which part of the IP address represented the network that you're on, and which part of the IP address represented you, a specific host on that network. That was the early days of IP addressing. It was the days of classful addressing, which means that the IP addresses could be put into a certain handy-dandy class, and you can infer things about the address based on the class. This was January 1st, 1983. It was known as Flag Day, when we turned off the old protocols that were being used, NCP specifically, and we turned on this new thing called TCP/IP, the Transmission Control Protocol, Internet Protocol Stack. January 1st, 1983, we turned it on. And around 1991, where were you guys in 1991? I don't think so. So around 1991, we realized that this classful system wasn't going to work, and we needed a better way to do this IP addressing thing. So that's why we went from classful addressing, talk about that in a second, to classless. So if somebody stops you on the street and says, are you a classy person or a classless person? From a networking perspective, you're very classless. You should be very classless. We've all been classless since 1991. So the IP address by itself, you cannot anymore today, since 1991, look at it, and know which portion represents the network that you're on, and which portion represents you, a specific host on that network. We need another form of an address. We need another identifier, and that's what this is, a subnet mask. No, that's, by the way, I got my switch wearing the mask too over here. That's not a subnet mask. This is a subnet mask. Under the net, no, that's not a subnet mask either. These are subnet masks right over here. If you take a look, the subnet mask can be expressed in, I like apple cider, classless interdomain routing notation, the slash notation, or and also dotted decimal notation. And again, underneath the hood, everything is a bunch of ones and zeros. So for the subnet mask, if you take a look, let's take a look at this one over here, /24, which means out of the 32 bits that represent the subnet mask, IPv4 addresses are 32 bits long as well. The first 24 bits of that subnet mask are ones. That's the /24. The rest are zeros. Here's what a subnet mask does. You take your 32 bits of the IP address, write them across. You take the 32 bits of the subnet mask, you write them right below, and you perform the logical AND process. You guys know about AND, you know Boole and James Bullion. You know Boole went to restaurants and he annoyed the waiters and the waitresses because he would actually take the menu and he would go down the items on the menu and he would just say true, false, false, true. And he left a big tip at the end though. So you're going to take the IP address bits and the subnet mask and perform a logical AND process. What that means is if you take, as you take a look at this little schematic over here, the IP address is in black. The subnet mask is in blue. So let's take these 32 bits over here. Let's logically AND them with these 32 bits right over here. And of course, with the logical AND operation, if the first bit and the second bit is a 1, we produce a 1 on the output. Otherwise, we produce a 0 on the output. So if you take a look at this orange stuff that shines through, when you take the IP address and the subnet mask and you perform the logical AND, not add, but AND process, what results is what we call the network ID. And what is really happening is the ones in the subnet mask mean the corresponding bits in the IP address are network bits, and they're shared by all devices on that network, sort of like an area code or a zip code. The zeros in the subnet mask mean that those corresponding bits in the IP address are host bits and are unique in totality to each device on the network. So when we take the IP address and the subnet mask and we perform the logical AND process, you see it in binary over here, you see it in base 10 over here. That means if you got some device with an IP address of 10.0.0.1 and the subnet mask of, what would the CIDR notation be for this? 255.0.0.0. What would that slash notation be? /8, absolutely correct. The network ID is 10.0.0.0, which means every device on this network has a first octet of 10. Every device on this network has the first 8 bits of the 32 bits as this pattern right over here. 0.0.0.0, 0.1, 1.0.1.0. So far, so good? So the very first thing a device does before sending traffic is to determine how far the traffic needs to go. In this example, Mr. 10.0.0.1 wants to send traffic to, this is 10.0.0.2. So here's what happens. Before every outgoing piece of traffic, the source takes its IP address and its subnet mask, performs the logical AND process, and comes up with its network ID. Oh, I'm on that network. So the source says, oh, I'm on 10.0.0.0. Then the source takes the destination IP address and uses its own, the source, subnet mask, and also performs the logical AND process. And as a result, if you take a look, in this case, 10.0.0.1 ANDed with 255.0.0.0, as well as 10.0.0.2 ANDed with 255.0.0.0, the way the logical AND process works, will produce the same network ID. If the network IDs are the same from both of these logical AND processes, the source knows that the destination is on the same network. Now you might say, well, why doesn't the source take the destination mask? Well, 2 reasons. Number 1, it never gets it. And more importantly, number 2, it doesn't need it. Because if the source and the destination are on the same network, what can you say about the masks? They're going to be the same. Watch what happens now when I flip the script a little bit. Watch this. I'll toggle. 10.0.0.2, the destination, has now been replaced with 11.0.0.2. And if you take a look at the binary section down here, the only difference, of course, between 10 and 11 in binary is the ones column in the first octet. So now we got a little different outcome. because now the source says, I am on the 10.0.0.0 network. The destination is on the 11.0.0.0 network. And I can't deliver the traffic directly. I'm going to need some help. That's how the source realizes that it's remote communication and it needs to get the attention of whom? Who does the source need to get the attention of whom? Who now? I like when people talk to me. Starts with an R or a DG. Right, the router, the default gateway. Absolutely. The default gateway is responsible for taking traffic off your network and bringing traffic from other networks on your network. Now, at this point, we're going to assume that the source either knows what the actual destination IP address is. Somebody might say, hey, this is my IP address, go ahead and ping it or send me traffic. Or, one of my favorite protocols of all time, DNS, Domain Name System, is going to give it its corresponding IP address. What's the IP address of the rit.edu web server? It's 129.21.14. That's the actual address. But DNS will do that behind the scenes. But there's a problem now, because if IP addresses are logical, software-based, hierarchical, and geographical, one day I could have a particular IP address here on the RIT wireless infrastructure, and the next day you could have it, and the next day she could have it, and the next day he could have it. How do we know which device is in possession of a single IP address at any point in time? That's where we got to go down in the OSA model from layer 3 to layer 2. Talking about the NIC, the network interface card, specifically with one of its inherent features and pieces of information, the MAC, Media Access Control address. MAC addresses, so different than IP addresses. They are not logical. They are physical. They're also known as BIA addresses, burned-in addresses, to the actual NIC when the NICs are actually made. They're not software-based. They are as hardware as they get. And there's no hierarchy of MAC addresses in terms of putting you on a certain network or on another network. It's a flat addressing space, and it is certainly not a geographical address. MAC addresses consist of 48 bits written in hexadecimal, base 16. And if we've got 48 bits and each hex digit represents 4 bits, as you can see right over here, we got 12 times 4. We got 12 hex digits comprising the MAC address. The MAC address consists of two parts. The first is known as either the OUI, the organizationally unique identifier, or the vendor ID. And the second part is like a serial number or a device ID. So if you're a NIC manufacturer, you do need to register for a prefix to make your NICs. And of course, many vendors like Cisco and Intel that make lots and lots of NICs have registered and have acquired multiple prefixes. So when you are connecting to a network through your NIC, whether it's wireless or wired, that NIC will come burned in with a particular hardware-based address. Of course, you can spoof it and all that stuff, but we're not talking about that today. Now, in terms of local communication, okay, the IP address is fine, but how do I know which device is in possession of a particular IP address? That's where you need to use a protocol known as ARP. Stands for Address Resolution Protocol. And here's how it works. Let's follow the story over here. Host A knows what its MAC address is, of course, because it's burned into the NIC. We'll just call it 12A's right over here. Host A also knows what its IP address is. It's host A. It knows what its addresses are. Host B, in this case, again, does know what the destination IP address is, but host A does not know what the destination MAC address is. So what host A does is it sends a broadcast, which is heard and received, forwarded by the switches, by every device on the network saying, if your IP address, in this case, is 10.0.0.2, I need your MAC address. Does that sound familiar? That's like some person standing on the stoop on a Sunday night with a microphone hooked up to a 500-watt amplifier saying, hey, Bob Smith, if you're Bob Smith, I need to have your street number. I disturbed everybody in the neighborhood, woke up all these kids that were sleeping, but you know what? I did get Bob Smith's attention. And as a result, Bob Smith sent me an ARP reply back. So the ARP request is a broadcast that is heard and processed by all devices on the network, saying if your IP address is, and in this case, the destination IP address of 10.0.0.2, I need your MAC address. Remember, Bob Smith didn't broadcast that address back to me. Bob Smith sent a unicast. He walked it over. He sent a direct message to me, one-to-one. One source, one destination. Nobody else in the neighborhood heard him talking to me. So the ARP request, while it is a broadcast, because it's got to reach everybody on the network, because I got to find who I'm looking for, the ARP reply is a unicast message, which is only received by the device that sent the ARP request. And after that ARP reply, host A knows that host B's MAC address, we'll just call it BB, 12B is right over here. And now host A can send the actual traffic with the layer 3 IP address in the packet encapsulated inside of the layer 2 frame with the destination MAC address. How are we doing so far? Excellent. Okay. Now, if you take a look at the schematics of the switch, switch has a table in RAM. It goes by a few names. Cisco calls it the MAC address table. In other circles, it will be known as CAM, Content Addressable Memory. It's also known as the SAT, Source Address Table. Every time a device sends traffic into the switch looks at the source MAC address and says, oh, that's your source MAC address? What port am I hearing you on? For instance, Fast Ethernet 0/1 is what Fred's MAC address is heard on. And the switch will now associate the source MAC address along with the port on which it heard from that particular source MAC address. So when the ARP reply comes back, let's say Fred sent the ARP request looking for the MAC address of Barney. Barney sends the ARP reply into the switch, and it's at this point the switch knows that Fred, with that particular MAC address, Cisco actually uses this dotted triplet format where it has 4 hex digits separated by 2 dots. Very unique in terms of how MAC addresses are represented. Windows uses dashes. Mac OS and Linux systems use a colon in between the 2 hex digits. That's just a formatting thing. But if you take a look, if the switch knows where you are, it just sends the traffic out of that port and not all the other ports. From an efficiency standpoint, that's great. And of course, from a security standpoint, that's even better. As soon as you send traffic into the switch knows exactly where you are. So eventually, looking at the source address tables of each of these 2 switches, each of the 2 switches know where all 4 of these devices are. And you'll also notice that Wilm and Betty, plugged into switch 2, have their MAC addresses associated with port GIG01 on switch 1. So let's take a look. It's the 3s and the 4s, because that's where their frames are entering switch 1, whereas Fred and Barney's MAC addresses are going to be learned on GIG02 of switch 2, because that's where those MAC addresses are being learned on switch 2. And as long as the switch knows where you are, the switch treats it like a virtual circuit. So in this case, Fred's message only goes out of the port associated with Barney's MAC address as opposed to the other interfaces on the switch right here. Now, in terms of remote communication, again, the source will realize that the destination network is not its current network that it's on. And it realizes, like I realized, I'm not going to drive my mom's candlesticks all the way back to Staten Island again. I'm going to Google for the nearest UPS store what would be the equivalent in the world of networking for the local UPS store. Same answer as before. Router! The router, or the default gateway, absolutely. So in this context, let's say that 12001, one of these devices over here, wants to send traffic to 14001, one of these devices right over here. When it realizes after the 2 logical AND processes that the 2 network IDs are not the same, what's going to happen is the source will send out an ARP request, which is a broadcast. It goes to all of the devices, including the router interface. Routers don't forward broadcasts. Routers stop the broadcasts from flooding out of the other interfaces onto other networks, but the router still will process the broadcasts. So what this router interface will do is it's going to look at the ARP request like the other devices on the 12.0.0.0/8 network. And this router interface will say, hey, somebody wants my MAC address. And this router, like in story number 1, the local communication story, will send an ARP reply back to the source with its MAC address. So now let's think about this for a second. The source is 12.0.0.1 over here. The destination is 14.0.0.1 over here. Those are the layer 3 IP addresses in the outgoing packet. Packets never move by themselves. Packets always move encapsulated in frames at layer 2. So what's going to happen now is the source MAC address will be the MAC address of the actual device sending the traffic, but the destination MAC address will not be this guy's MAC address right over here. It's going to be the MAC address of the source's default gateway. And the traffic will be sent over here, just like I brought the package with my mom's candlesticks to the local UPS store. Now, the local UPS store is going to see that the final destination represented by the IP address is not where this package is where it needs to be. So the local UPS store will look up in its routing table the next UPS facility to send that package to, and it finds the next facility. In this case, R2 realizes that the next facility is accessible through this interface right over here of R1, and will actually send an ARP request saying, hey, if your IP address is, insert IP address of R1's interface here, send me your MAC address. So this interface of R1 will send its MAC address to R2, and now R2 will send the original packet, but now that original packet will be encapsulated in a new frame. Look at the destination MAC address, just going up the line, and I'm using 2 hex digits that don't make any sense instead of the actual MAC addresses for space purposes. But let's say this MAC address here is DD, and let's say this MAC address here is CC. So now the MAC addresses are different in the frame than they were before, but the IP addresses are still the same. You guys see that? This is the second important reason why we need both layer 3 IP addresses and layer 2 MAC addresses. The first reason was, who has that particular IP address at a time? Oh, it's that device with that MAC address. And now you can see from the routing perspective, MAC addresses are needed to represent the step-by-step hops your packet takes to reach its final destination. So just like if you're tracking a UPS package, there's a sticker that's slapped on the box, and that's how you track your package, scanning out of the first facility, scanning in of the new facility. That's exactly what that sticker represents, the MAC addresses. R1 now will look at its routing table, and these are pseudo routing tables for each of the routers over here, and realizes that to get to the 14 network, it's got to send the traffic to R4. And again, an ARP request and an ARP reply gets the packet to R4, but look at this now. The source MAC address is going to be R1's interface over here, and the destination MAC address is going to be R4's MAC address right over here. And again, another sticker is slapped on the box. Scan in and out of the new facility. Until R4 says, wait a minute now, that destination network, I'm actually connected. I'm connected to it right over here. That's like when the candlestick holders candlesticks get to a UPS store in my childhood zip code. At that point, they put it on a truck and they bring it out to my childhood home. That's what happens over here. For the last time, the frame is recreated. And now the source MAC address is going to be the default gateway of the destination, in this case, GG. And the destination MAC address is going to be the actual MAC address of my childhood home in Staten Island, or the actual destination over here, Mr. 14001. So that's another important reason why we need both layer 2 MAC addresses and layer 3 IP addresses. Any questions so far? Every time a packet passes through a router interface, that outer layer, the frame, is stripped off, and the resultant packet is reframed. And every time you have a new frame go on a packet, of course, there's a new source MAC address and a new destination MAC address. But wait a minute now. if the physical way in and out of the machine is through a NIC, the network interface card, and it is, that's how those ones and zeros get in and out of your machine. How do those ones and zeros representing some meaningful information logically get into your machine? Well, the logical way in and out of the machine is through a program, which is lines of code that follow algorithms to solve a problem or accomplish a task. Okay. So we got these programs. You ever hear the term service? It could be a client service. It could be a server service. A service is a program that runs in the background independent of assignment. In the world of Linux, we use that word instead, daemon. And of course, there's crazy words that are used in different contexts. Service is one. A Windows service is what I described, but a Linux service is crazily enough a program that launches a script to run a daemon. So service in Windows and service in Linux, they mean completely different things. The executing program can be broken down into its smallest unit of execution, known as a thread, and every running program, of course, is running in a process environment of itself with its own stack and heap allocation. We'll talk about that another time. And you have to throw those onto the board before we talk about this very important thing right over here. If the physical way in and out of the machine is through the NIC, the logical way in and out is through a program or a service, as we talked about. How do you get into a program or service? It's through one of these ports, which is, you could say port, you could say port number. The numbers that represent logical communication endpoints, which means if you start an Apache web server, port 80, hopefully not, but port 443 instead for cryptography will be used, will be open. Stop the Apache web server, port 80 or 443 is closed. Start a FileZilla FTP server, port 21 is open. Stop the FTP server, port 21 is closed. Server services use well-known ports so that client services can easily access them. Clients use dynamic ports on an as-needed basis, and when the communication is done, those dynamic ports that are opened up by the clients are closed. So if you take a look over here, this is Frank and this is Helen. They both live in the same apartment building. They're checking their mail. They're good friends. Frank over here lives in apartment 21. Helen over here lives in apartment 80. If you want, write each of them a letter. You got to put their street address, 567 Main Street, Anytown, New York, USA, 12345. Frank lives in apartment 21, so you will have to put apartment 21 over there on his letter. Helen lives in apartment 80, so you'll have to put an 80 on her letter. So the obvious question is, how does Frank get his mail? How does Helen get her mail? If they both have the same street address, that's like them both sharing the same, let's say, MAC address and IP address. But the mailman puts Frank's mail in box 21. He puts Helen's mail in box 80. You know what their full names are? I actually do know their full names. His full name is Frank Thomas Peterson, right? FTP. And this is Helen Teresa Thomasina Parker, HTTP. So the operating system will look now at the layer 4 information. Oh, we got addressing at layer 2 MAC addresses. We got addressing at layer 3 IP addresses. We have a form of addressing now at layer 4 ports or port numbers, which represent the program or service on the machine that the traffic is coming from and on the destination where the traffic is going to. That's how the operating system gets traffic to your FTP server and your web server if they're both on the same machine. And of course, sharing the same MAC and IP addresses. Like we mentioned, there are a few different ranges of IP addresses. For time purposes, servers use port numbers in this range over here, the well-known ports. Clients use ports in the dynamic range over here, the registered ranges. Sorry for a different day. So if you got packets at layer 3 holding the IP addresses, and you got frames at layer 2 holding the MAC addresses, we need something at layer 4. After the frame is stripped off, after the packet is stripped off, by the way, that smells good. Making my stomach go hungry here. To hold those port numbers, and in the world of networking traffic, it's either going to be in the form of what we call a TCP, Transmission Control Protocol segment, or a UDP, User Datagram Protocol. We just say datagram for the intended redundancy over here. You, the human, don't choose which layer 4 protocol will be used. The sending application will actually make that decision. So here's a little bit about the differences. TCP has a lot of overhead. UDP has no overhead. TCP is connection-oriented communication. UDP is connectionless. And people lie to you. They say there are only two things that are guaranteed in life, death and taxes. You can quote me on this. People have, actually. There are three things that are guaranteed in life: death, taxes, and TCP. It's as guaranteed, if not more, than death and taxes. Think of UDP as putting a stamp on a letter, putting it in a post office box, and if it gets there, it gets there. If it doesn't get there, it doesn't get there. You don't know that it got lost, and the destination doesn't know that you sent that person a letter. You guys ever do that, by the way? I can't remember last time I did that. But with TCP, that's where at the post office you pay, what is it, an extra 38 cents for that green and white sticker, the return receipt. When that letter is handed to the actual destination, they sign something and they let you know that they actually got it. So if TCP is connection-oriented, acknowledged delivery, and it's guaranteed, and UDP is connectionless, not guaranteed, and not acknowledged, which one is better? Which one is better? That's the answer I'm looking for. What are you going to wear when you're 90 years old? Depends. So which is better? Depends as well. For data integrity, where you've got file transfers, or emails, or print jobs, or anything like that, where if one bit is changed, it could corrupt the message or compromise the integrity, the sending application will always choose TCP. If you're dealing with a Twitch stream, or a Zoom stream, or major networking protocols like DNS and DHCP, UDP is used. In other words, we want speed, and if a piece of traffic gets lost, who cares? If it's a stream, it's a fleeting moment in time. You might notice a degradation in video or audio. It's going to be for a small little glitch. Nobody's going to realize it anyway. Or if you're in class and you won't have this problem with me. If you raise your hand and your teacher doesn't your professor doesn't call on you, or the professor gives you some crap answer, and you're like, huh, what? Ask again. That's my recommendation. You could quote me on that as well in your other classes. So UDP, if the message isn't delivered, if you're querying a DNS server or DHCP server, you just ask again if you don't get a response. We do that instead of incurring the penalty of the high overhead, which we do want for communications that involve integrity and accuracy. So either the TCP segment or the UDP datagram will contain, the only thing they really have in common is this port number. Unfortunately, it's not going to be capturing well on the stream. But. So that's an example of UDP, where the traffic is just sent. And if it gets there, it gets there. If it doesn't get there, it doesn't get there. And we have no idea on how it works in any case. That's TCP. By the way, this is the only real-world use of expo markers nowadays. But I need a partner. Yeah, come up to our stage here in the studio audience. Say hi to the camera.
Hi.
Tell the camera your name.
My name's Lucas.
Social security number?
No.
Mother's maiden name? Street you grew up on? Okay. So this is going to be an example of TCP. Hi, Lucas. I'm Jonathan. Can I send you some markers? Yes. So he says yes. And now also say, can I send you some stuff as well? Say.
Can I send you some stuff as well?
Sure. So I just gave him the black marker. Say, I got the black marker. Say it.
I got your black marker.
And by the way, this is not a wired connection, so it's just.
I got your blue marker.
And by the way, TCP can recover from stuff like that as well. Drop it backwards.
I didn't.
Well, you don't know that you didn't get the red marker. So if he told me he got the black marker, and he told me he got the blue marker, and he didn't tell me he got the red marker, what I'm going to do is, as a sender of traffic, as the source of traffic, this is what TCP does. It takes the outgoing traffic, caches it in RAM, and waits a little bit. Oh, actually on schedule. And waits a little bit for the acknowledgement back. If that acknowledgement timer expires, oh, he didn't tell me he got it. I'm going to take that exact piece of traffic out of RAM and sense it again. And now he said, what did he say?
I got your red mark.
I got the red mark. A round of applause for Lucas, our TCP. So the way that TCP does that is with something called the TCP three-way handshake, which I'll teach you about in NSSA 245 network services. But for now, I should also tell you that TCP also, besides this orderly startup process, the three-way handshake, which is affectionately known as SYN-ACK, you're familiar with that, which represents the flags that are turned on in the TCP header, also has a very calm, cool, and collected teardown process using the fin or final flag. FIN-ACK, FIN-ACK. So when I teach that in net services, then we eventually start class with SYN-ACK and FIN-ACK, FIN-ACK, and that's how we end the class. Also, there's another flag called the reset flag, which is a quick termination. Instead of saying, oh, yeah, nice to talk to you, very nice talking to you, gotta go, goodbye. That's the orderly way that TCP ends a particular connection-oriented session. It sends a reset flag, which means, shut up, I gotta go, bye, which is what I'm gonna do right now. Thank you.